Hi everybody, welcome to this week's lecture. This week we're going to be talking about ensemble methods and random forest in particular. So what we'll cover tonight is ensemble methods, which are really sort of the leading edge kind of area of data analytics in a lot of ways at the moment. Then we're going to look at three examples. The first is bagging. The second is a method that's based on bagging called random forest, and this is one of the classifiers that we use quite frequently because it's easy to use and it doesn't really take many parameter settings that you need to set, and it's quite resistant, or it doesn't mind what values really you use for the parameter settings. And then we'll very quickly look at another method called boosting, but we're not going to go into that in any detail really. So first off, ensemble methods. So we've already looked at decision trees previously, and you'll remember that they're a single classifier that are trained from some data set, or training data. So it's one classifier on its own. What we're going to look at today, though, is classifiers that are constructed from a whole lot of different classifiers. So the idea is that we train a whole lot of multiple classifiers to solve the same problem in slightly different ways, and then they all vote. When we need to classify a new data point, they all vote on the answer, and then we take the class value whose vote wins. So the general idea is to construct a set of base classifiers from the training data. Then when we want to predict the unseen data, we combine the predictions of all the base classifiers together by voting. So why would we want to do this? Well, it turns out that ensemble methods tend to perform better than any one single classifier on its own. Also, there's something quite nice about them, at least with the bagging and the boosting. They don't really depend on any one type of classifier. So we could use decision trees, neural networks, support vector machines, or a whole lot of different methods for, say, bagging. We can even combine classifiers from different methods together into the same ensemble. So they're often called a meta-learning method. The rationale behind them is as follows. Now let's say that we have an ensemble of 25 classifiers, so binary classifiers. They're going to classify between, say, true or false. And each one has an error rate of 0.35. So each of those individual binary classifiers, the 25 classifiers, has an error rate of 35% or 0.35. And what we're going to do is take the final prediction to be the class that has the majority vote. Now, if the 25 classifiers are all exactly the same, let's say they're decision trees, if they're all exactly the same decision tree, then the error rate of the ensemble, of the group of them together, is going to be 0.35 as well. Because if you think about it, they're all going to, if they see a test data point to classify, they're all going to classify it in exactly the same way. They all act in the same way. But if the classifiers are independent, if the 25 classifiers are all trying to solve the same problem but in slightly different ways, then the group of them, the ensemble together, only makes the wrong prediction if more than half of the base classifiers get the answer wrong. And if you think about that, if they're all working in slightly different ways, then you're going to get a better result because they'll all make slightly different errors. So the ensemble classifiers will do better than individual classifiers when two things happen. First off, the base classifiers have to be independent of one another. So the base classifiers have to be a little bit different from one another. And second, the base classifiers have to do better than just doing random guessing. So as long as you have those two conditions, ensemble classifiers tend to do better. So this diagram is the general approach for how we might do ensemble classifiers. So at the top we have a data point. At the top we have our original data set. So the first step is to create multiple data sets from that original data set. And there's what we can do with ensemble methods is it's a whole lot of slightly different approaches to doing each of these steps, and you get slightly different results. But let me just talk about the general approach. We have our original training set, and we create multiple data sets from that training set. And usually those multiple training sets are slightly different. Second stage is to build a classifier for each of those separate data sets. So we build classifier 1 for dataset on dataset 1, classifier 2 on dataset 2, and so on to classifier T on dataset T. Then finally, we combine the classifiers in some way. And the combining is the bit that we do with voting. So there's several approaches for constructing ensemble classifiers, and I want to work through each of these in turn because you get slightly different kinds of ensemble classifiers depending on how you work. The first thing we can do is work with the training set. And if we do that, we get two different methods. And these are two of the methods we're going to look at tonight. That's bagging and boosting. So here, we make those separate D1, D2, D3, all the way up to DT data sets in different kinds of ways of sampling. So working with the training set, we can get bagging and boosting. Second of all, we could work with the input features. So we could choose different combinations of features, input features to build our base classifiers. And when we do that, we can get random forest does that approach. It also uses bagging, but random forest definitely plays with the different kinds of input features that are allowed. Another approach is to work with the class labels. So here they group combinations of classes into different binary classifications, and if you do that, there's a method called error correcting output codes that result. And the other approach is to work with the learning algorithm. Here we just use either different parameters of the learning algorithm for each of the base classifiers, or we randomize them in some way on the same data set. So you can see we're trying to get slightly different base classifiers. So we can do that by either fiddling around with the training set, using slightly different D1s to DTs, by playing around with what input features we allow the base classifiers to train on, by playing around with the class labels, or by changing the parameters of the learning algorithm. They're all ways that we can make each of the base classifiers independent of one another. So these first three approaches are generic. They don't depend on the kind of classifier that you use. So in that case, then a meta classifier. The last depends on the type of classifier, so it doesn't always work. You need to have the right kind of classifier to be able to play around with the parameters. Now, ensemble methods work best with something called unstable classifiers. So these are classifiers that are sensitive to minor changes in the training set. In other words, in some ways they've overtrained on the training set. So, for example, artificial neural networks or decision trees that we don't prune, that we allow to grow all the way through. So ensemble methods work best with those, and we'll see why that's the case a little bit later. And then finally, the predicted class from the ensemble classifier is obtained by voting. So each of the base classifiers votes. And there's two main ways of doing this. Either each base classifier gets one vote, so each one gets one vote each, and then you just take the majority, or you can allow some base classifiers to have more or less weight for their vote. And you can set the weight so that it's related to how good the base classifier is at solving the problem. So base classifiers that are really good at solving the problem get a big vote, and base classifiers that are crappy get a much smaller vote. And we'll see two examples of this with bagging and boosting. The general procedure then is to start with D, the original data set. K is the number of base classifiers, and we have a test data set T. Then for I equals 1 to K, so for each of the base classes, we create a training data set D sub I from the D. Then we build the base classifier C sub I from the training set D sub I. We do that for each of the K classes, base classifiers. Then for each test record in our test data set, we vote we apply each of the base classifiers to the data point, and then we take the vote, and that's what we return. There's a couple of disadvantages with ensemble classifiers. First off, ensemble classifiers might be more susceptible to overfitting. That's not always the case, but sometimes they are. And as we know, that's not a great thing. And the other disadvantage is that the resulting ensemble classifier, although it's generally more accurate than each of the individual base classifiers, it's much harder to understand because you're now taking knowledge from a whole lot of base classifiers and you're trying to work out how it works together. Remember, with the decision tree, we can pretty much see how it's solving the problem. But with if we have a whole ensemble of base decision trees, then we can't really understand the whole together. It's a bit trickier. Let's look now at the reason that ensemble classifiers work. Now, you've seen this before. We talked about this last week. This is the bias variance decomposition. So you remember that the test error can be divided into three components. There's a bias, a variance, and the noise. The noise is the underlying sort of issues in the data that we can't really get past, but the bias and the variance depend on our classifier. The bias is how well the model can do for any training set. So remember that if we have simple models, like say a linear model, then it's very biased because there's not much difference between what it predicts for lots of different training sets. And if we have a more complex classifier that can understand subtle patterns in the data, then the bias is less. Variance is all about how sensitive the classifier is to any particular training set. So if a classifier has high variance, and usually classifiers that are very flexible or have many parameters that means that they'll do quite well on a particular training set, but on other training sets they won't do as well. And you remember that's related to overtraining. And noise we've already talked about. And we've seen this slide before as well. So as a model becomes more complex, the prediction error on the training data goes down, and at some point, and also for the test data, but at some point it starts to increase on the test data, and that's where the model has started to overtrain, and that's where the variance kicks in. The reason that ensemble methods do well is because they can reduce the variance part of the error, and that's because they're looking at lots of different training sets, so that overall the ensemble method isn't as sensitive to different training sets. Let's look at our first kind of ensemble method, and that's bagging. So bagging stands for bootstrap aggregating, and the idea is we're going to make our training sets D sub I by repeatedly sampling with replacement from the original data set D. So for example, our original data set has 100 records, and our training data set D sub I, we sample 100 records from the training data set, the original data set D, but we're allowed to choose the same data point more than once. So that means that some data points are in there more than once and some are not in there at all. So that's called a bootstrap sample, and that's why we're saying bootstrap aggregating. So on average, when you do that, each of the D sub I training sets has about 63% of the original data points from the original data set. And then what we're going to do is, for each of those D sub I's, we just train a classifier and then classify the instances by using the majority vote. Let's look at an example now. We're going to do a binary classification, so predicting 1 or -1, and we're going to predict a y from our x. So here's our data set. It's really simple. All we've got is one input attribute, and that's called x, and our training set has values 0.1 all the way up to 1. And our y is 1 or -1. And you can see that everything under 0.3 and under is a 1, and anything from 0.8 above is a 1, and anything between 0.4 and 0.7 is a -1. So we're going to use something called decision stumps as our base classifiers to make this prediction. And a decision stump is just a one-level decision tree. So it just has a root and the two children, which means it can only have one test condition. So x is less than or equal to k, where k is some split point. And we're going to choose the k to minimize the entropy of the leaf nodes. That sounds complicated. All it means is we're going to choose a k so that most of the data points on one side of that split point are the same class. So without bagging, the best decision stump that we can do is either a split at x equals 0.35 or at x equals 0.75. So if we have x is less than or equal to 0.35, then everything on the left-hand side of that will be a 1, and everything on the right-hand side would be classified as a -1 because there's more -1s than 1s on the right-hand side. And you can see that the accuracy of that will be 70% because it gets 7 of the data points right and 3 wrong. The same if we have x is equal to less than or equal to 0.75. So then on the left we would have a classification of -1 because there's more -1s than 1s, and on the right hand side we'd classify them as 1, and again it gets 7 right and 7 wrong. So the best thing that we can do with a decision stump that can only have that one test is the accuracy of 70%, 0.7. So let's look at how we can get a better result if we use bagging. So we're going to just do 3 bootstrap samples. So usually this is way fewer than you would normally use, but I'm just trying to illustrate how it will work. And I didn't want to do 20 of them, it'll be too boring for you. So we'll just do 3 bootstrap samples. So here's our bootstrap samples, and also the decision boundaries that make sense. So you can see that in bootstrap bag 1, we've chosen 0.1, 0.2 we've chosen twice, 0.3 once, 0.4 we've got twice, 0.5, 0.6 once. We didn't get 0.7 or 0.8 or 1, but we got 0.9 twice. And using that data set, the best split that we can do is at 0.35. And in that case, we would classify the left-hand side as a 1 and the right-hand side as a -1. And you can see that if we did that, we'd get an accuracy of 80%. And with bag 2, we've got 0.1, 0.2, 0.3, 0.4, 0.5. We don't have 0.6 or 0.7. We've got 0.8 and 0.9, and we've got 1 3 times. So again, if we do a decision, if we try to split the data there, the best split we can do is between 0.5 and 0.8. So we would just take the midpoint between that. And then similarly, we've got a third bootstrap sample, and we've got a split at 0.75. So when we would do our classifications, as I was saying before, on the left-hand side we'd do 1, right-hand side -1, and so on. So what we're going to do now is classify all of the points in the original data set, so the 0.1, 0.2, all the way up to 1, and then we're going to vote with each of the decision stumps and then see what the majority vote will be. And this is what it looks like. Now this is a bit complicated looking. What's it showing? So on the top line, we've got our original x values, and then on the second line that says 1, that's the classifications that our base classifier 1 would give us. The second one is the classifications that our base classifier 2 would give us, and the third one is the classifications that our base classifier 3 would give us. And what we're going to do is just take the majority vote from that. So for the 0.1, we've got 2 1s and a -1. So the class at that very end is at the very bottom row on the left-hand side is 1. There's 2 greens and 1 red, so we choose a green. Same with 0.2 and 0.3. There's 2, for those data points, there's 2 greens and a red, so we choose the green. 0.4, there's 2 reds and a green, so we choose red, and so on. And you can see that if we do that, the Each of those ensembles, each of those base classifiers on their own, it doesn't solve the problem properly, but together as an ensemble, they're 100% accurate. So this sort of shows how we do this base classification, how we do the ensemble classifier for bagging. So the reason they work is that ensemble methods enhance the representation of the target function. So in the case that we were looking at, the individual base classifiers are really simple. They can only be this one test, but the ensemble, so they're not able to represent the function. We could say that they're too biased in a lot of ways. But it turns out that the ensemble of them together can understand those more subtle relationships because we've enhanced the representation. So bagging improves generalization error by reducing the variance component of the base classifiers. As every sample has an equal chance of being selected in the bootstrap sample, bagging doesn't focus on any particular instance, so that means it's less likely to overfit when we apply it to noisy data. The performance that we get from the ensemble depends on the stability of the base classifiers. So if we have unstable base classifiers, so ones that have high variance, so they've overfitted the data, then when we do the bagging, we have room to reduce that variance component of the error. If we had stable base classifiers, the error is mostly caused by a large amount of bias. So ensembles can't reduce that bias, so that means that bagging won't really help to solve the problem because all they can do is reduce the variance component of the error. In fact, it might be a little bit worse, as you can see from the slide. Let's look now at another method called random forest. So as the name suggests, random forest is an ensemble classifier of decision trees. What do you get when you have a lot of decision trees together? You get a random forest. And the way that they work is by combining bagging, which we've just seen previously, with random selection of attributes. Random forests was developed by Leah Breman and Adele Cutler in 2001, and they've got two main parameters, although I've only listed one here. The main parameter is M, which is the number of attributes that they're going to use to build the decision tree. And we'll see that in a minute. Usually you choose M much, much less than the number of attributes. So if you have often there's rules of thumb where you'll take the square root of the number of attributes. So take quite a lot less attributes. There's also one other parameter, and that's the number of decision trees in the forest. So there's two main things, number of decision trees and the number of attributes to choose. This is how the algorithm works. So given n training points and m variables, and b is the number of trees, and little m is the number of random attributes to choose, what we do is, for each of the trees that we want to build, b, we're going to do one. First off, create a bootstrap sample of d sub b of n, so we choose the same number of data points. So that's exactly like we did with the bagging beforehand. The second thing we do is to build a decision tree to classify that training set d sub b, but at each of the node, we're only allowed to choose the split variable from among little m variables, chosen at random from the possible ones. So we're reducing the number of variables that we're allowed to use to build a decision tree. And we're not going to prune the tree either. The reason we sort of limit ourselves to choose less possible attributes to split from is because we want to bias these trees to be slightly different from one another, and this does that job quite nicely. Then, so we build our forest. To classify a point, we're going to take the majority vote from the trees in the forest, exactly the same way that we've done with the bagging. So, bagging, or the bagging component of random forest, choosing these bootstrap samples makes the classifier robust to noise in the training set. And the random selection among the little m attributes makes the classifier robust and it allows it to deal with data sets with many attributes, and it's also computationally efficient. Makes the classifier robust because we're limiting, we're making sure that it's going to choose the right attributes. Because we're not going to prune the trees, that means that we get classifiers that are less biased and also have a higher variance, so that the ensembling will be able to reduce that variance component of the error and make it work. We can also do regression as well as classification, and if we do that, we just average the predicted values rather than taking the majority vote. So there's a lot of advantages with random forest. First off, they generally produce very accurate classifiers really quickly. If you don't know what else to do, random forest generally does a pretty good job. It can handle a very large number of attributes and automatically find the good ones. There's a bit of a trick with it, which we'll talk about in a minute, where random forest can automatically estimate which are the important variables in the data set. So it can work out a variable importance measure and rank the variables by their importance. And that is useful for you to understand what's happening in the data set. Another advantage is that it generates an internal unbiased estimate of the error, of the accuracy, or the test error, and you can use that to know when to stop building the random forest, so if you've built enough trees. This is a really useful thing, because if you think about it, what we've done with the decision tree on its own is we need that separate test set to be able to work out the accuracy of the classifier. So what I'm saying here is that random forest can automatically do that without having a test set, and that's quite a remarkable and useful thing. Random forest can deal with missing data quite nicely. It can handle data sets with unbalanced classes, or at least some versions of random forest can. The original random forest that Leah Breman and Adele Cutler developed can compute the proximity between data points, and there's a way to use it to visualize data, although you don't see that being done all that much. And there's also unsupervised versions for clustering and outlier detection, and again, you don't often see that around. Some more advantages. You don't need to do much pre-processing of data, so you don't need to do normalization. You don't really need to do too much feature selection because it can work out how to do that itself. It's resistant to outliers, and that's quite useful compared to other methods. If there's lots of input variables, then random forest targets the most useful variables, so we often don't need to do variable selection. So the data that I work with, the biomedical data with gene expression values, where we have thousands and thousands of attributes, we use random forest, and that does quite nicely. It tends not to overfit the data because many trees are built, and also there's two kinds of randomness in it, the bootstrapping and also the choosing of the data points, of the attributes. And the third thing is it can be quick. Fifth thing is that it's easy to parallelize, because if you think about it, you can build each of those decision trees from the bootstrap samples on separate processes. So because it's easy to parallelize, that makes it faster to run. There are some disadvantages. The first is that it can overfit some data sets. And the second thing is that it doesn't handle, when you have data sets with many, many, many attributes that are quite irrelevant, then it doesn't really handle them quite so well. And if you think about it, you can think about why that happens quite easily. If you've got many attributes that aren't relevant, then when you choose your lowercase m of them, more often than not, you're going to get attributes that aren't useful. And it's hard to get attributes that are useful or the ones that are useful together. So if you have only a few attributes that are relevant and lots that are irrelevant, it doesn't do all that well. Now, let's talk about this thing called the out-of-bag test set. So remember we said that the random forest is going to choose a bootstrap sample D sub B for each of the trees it's going to build. And remember we said when we do a bootstrap sample, on average you get about 63% of the original data points. Well, we can use the data that isn't chosen in a special way. So we've taken our bootstrap sample D sub B, and if we look at the data points that aren't chosen, we're going to call that the out-of-bag test set, or the OOB. And we have one of those for each of the trees, or each of the bootstrap samples that we've made from the original data set. And we can use this out-of-bag test set to do two things. First off, we use it to calculate that unbiased estimate of the test error. And second of all, we can use it to estimate the importance of the variables. So let's see how we can do that for each of those two cases. So first off, calculating the error estimate using the out-of-bag test set. So for each of the trees, about a third of the cases are going to be in this out-of-bag set. And we've got a different out-of-bag set for each D sub T. So what we're going to do, and of course we have a different D sub T, but we have a different OOB as well. So what we're going to do is classify the data points in the OOB. So what we do is this. For each case in our data set, we work out which OOBs that data point is in. We get the classifications for each of the trees where it's in that OOB. Then that gives us an error over all of the trees for the OOB for that particular case. And then we average the error over those trees to get a test error for that one case. Then we do that for all of the cases in our data set. So for each case in our data set, we get the error for the trees where it's in the OOB. And for the ones that isn't in the OOB, we don't worry about it. But for the ones that's in the OOB, we get the errors for each of those trees. We average them, and that gives us the error for that one data point. And then we do that for each of the different data points. And if we do that, that gives us an unbiased test error for the entire forest. And we can use that to know when to stop training the random forest, because as soon as it starts to increase, then that's an indication that we're starting to overtrain. The second thing we can do is to use the out-of-bag set to calculate the variable importance. When we grow the beeth tree, we work out the prediction accuracy of the out-of-bag samples using that tree, for that tree, out of that tree. Then when we want to define the importance of a particular variable j, what we do is we randomly permute the values of variable j in the out-of-bag set, and then we calculate the accuracy again. And if that variable was important for making the decision, then the accuracy is going to go bad. If it wasn't important, then the accuracy won't change. So then we average the decrease in accuracy over all of the trees, and then we can use that as a way to measure the importance of the variable. So a big decrease in accuracy means that that variable was important for solving the problem, and we can rank it more highly. So when we run random forest, we can often get a measure of the importance of the variables as either at least in R or Rationale, it's a mean decrease in accuracy or a mean decrease in the Gini index, which is the index used to choose the split point in trees. So there's several ways to do random forest in KNIME, and the first way is to use the random forest as it's implemented in Weka. So remember that KNIME gives you access to all of the Weka predictors. So the first way is just to use the random forest node in Weka, and then we use the Weka predictor. And there's several parameters in the configuration panel for random forest, and the two main ones are num features, that's that M that we talked about earlier, and num trees, which is the number of trees to build. There's a few other parameters as well, but you can read how they work. And then of course, as we did with the decision tree, we use predictor to make the prediction. The other approach in KNIME is to use something called the tree ensemble learner. And this is an experimental set of nodes that KNIME are developing, but they seem to work quite nicely. And if you read the help, they're quite configurable. There's lots of parameters. There's a whole lot of tabs of parameters that you can set in tree ensemble. And depending on how you set those parameters, you can get behavior that looks like or is similar to random forest. And if you read the help on the right-hand side of the panel when you select the tree ensemble learner, it tells you what parameter settings to use to get it to act like random forest. So just check the help for those parameter settings. So you might ask, which node should we use? Well, the Weka random forest node doesn't give variable importance scores, and they're fairly useful. So that's a bit of a downside with the Weka random forest. But there are attribute measures that are given for the tree ensemble node. Also, the Weka random forest node doesn't allow you to view the trees that are generated, and the tree ensemble does. Also, tree ensemble has many other parameters that you can play around with. So I'd probably recommend using tree ensemble. That said, if you download Weka and use random forest within Weka, you are able to see the variable importance scores, and and you can see them in that. I'm just going to quickly talk about this. If you're using random forest in Rattle, then it's quite easy to do. This is the model tab, and you choose forest, and you can see you can choose which type of decision tree to build, a traditional or a conditional tree. We can set the number of trees and the number of variables. We can use impute to impute the missing values. And this last bit that says sample size allows us to, if we have a very unbalanced problem, then we can use a parameter in there to balance it up again. When we hit execute and run the random forest, these are the results that you get. You get a couple of new buttons. Importance allows you to see the variable importance. Rules just allows you to see the rules that come out of it. That little number 1 allows you to see the rules for that particular tree. And errors allows you to look at the out-of-bag error. It's a graph that graphs the errors by tree. And so it gives you an idea of how many trees are needed. And you can see in this summary, this is the output that R gives about random forest. So the first bit is the call that Rattle makes. That's how you call random forest in R. The second bit is this out-of-bag estimate of error rate. That's the internal error rate. The next thing there is a confusion matrix, so you can see how it solved the problem. And then the bit underneath the variable importance. So for example, in this one, you can see that pressure 3 pm is ranked the highest, and it has the highest mean decrease in accuracy and mean decrease in Gini, which suggests that this variable is the most important for solving the problem. Okay, let's now really briefly talk about boosting. So boosting is adaptively changing the distribution of the training examples so that the base classifiers have to concentrate more on the ones that are harder to classify. And the way that it works is that it assigns a weight to each training example and then changes that as it goes through each round. And then the higher the weight, the harder the example it is to classify. So the weights are assigned to the training examples, and they're used in two different ways. First off, they're used as a way as a sampling distribution to get the bootstrap sample. So the idea is that if there's a higher weight, then it is more likely to be sampled in the bootstrap sample. And if it's lower weight, then it's less likely to be sampled. And it's used by the base classifier to learn a model that's biased towards the high weight examples. So the algorithm looks like this. Initially, all of the samples have a weight of 1 on n, so they're equally likely to be selected. Then a sample is drawn with replacement according to the weights to get the D sub t training set. Then we build a classifier, use it to classify all the members of the original training set, and then we update the weights based on whether the classifier was able to um, classify it correctly or not. So if the classifier wasn't able to classify it correctly, then we increase the weight, and if it was able to classify it correctly, then we decrease the weight. Then we go back to 2 and draw another sample. And we keep on doing that until we've done enough rounds. So rounds are like each of the base classifiers. And then the final ensemble uses a weighted voting to classify the new examples. So each classifier isn't given the same vote. The classifier is given a vote based on how well it did as a classification. We're not going to go into all the details of that, but we'll talk. I'll just show you sort of roughly how it works. So this is an example of these numbers are the samples that are chosen from the data set, and each row is the boosting round. So for example, in boosting round 1, we've chosen samples 7, 3, 2, 8, 7, 9, 4, blah, 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 blah. And what we can see is that some examples get chosen more than once because of the bootstrap sampling. And so for example, in the first round, we chose 3 twice and 7 twice. Now let's assume that example number 4 is hard to classify. So what happens is that it will get a higher weight in subsequent rounds, which means that it will be more likely to be selected in subsequent rounds. So you can see that it got selected 1, 2, 3 times in the second round. Also, examples that weren't chosen in the first round are likely to not be classified very well because the classifier didn't see them. So that means they'll tend to automatically get higher weights, and then they'll appear in later rounds. There's a whole lot of different examples of boosting, but one of the most common ways is called ADA boost. It's a common algorithm. Uses decision trees often, although it doesn't have to. And the different boosting algorithms differ in how they update the weights and in how they make the final predictions. So Rationale has this commonly used version called ADA boost. It's using decision trees or decision stumps. There's other versions in R. It's not so easy to do with KNIME. So that's it for this week. I'll see you in class.